Welcome back to IME 315. Last week we discussed interest equivalence, and we were talking about point estimates, something today and a single point out in the future. But we're going to talk about a unique subset of that this week, which is uniform series. So uniform series says we have points out in the future. There are several of them, and they're all going to be the same. So think about it like a home mortgage payment, where you make a constant payment every period, every month for 15 years or 30 years, or a car payment, where you get a loan and you make a constant payment on the car payment every period, typically every month. We sort of went over an example like that with when I had the four different ways of repaying a loan last time, and the four different ways, one of them assumed a constant payment of $1,280 some, I believe, for 5 years. And what we're going to go through today is you're going to understand at the end of this lesson how to actually model that and calculate those numbers. So we're going to discuss several problems, and then I'm going to show you spreadsheet solutions to these problems. So when we show a cash flow diagram, A is an end of period cash flow in a uniform series. Uniform means each one of these A, period 1, period 2, all the way out to period N are the same value. So they're uniform. And notice that they're end of period. So when deriving these formulas, the assumption is that the uniform cash flow is at the end of period. So if we borrow money today, that's end of period 0, and the repayment will start one period down the road. And we need to understand this because not all business problems are exactly like this, and we need to make adjustments in our calculations because the model formulation and the formulas assume end of period, and end of period 1 from today. So these things are like automobile loans, like I said, mortgage payments, insurance premiums, periodic payments, and we need to estimate future costs and benefits. And that's kind of the one takeaway that I sort of have glossed over in everything, is that the one thing you know for sure is today's number. Pretty much everything in the future are going to be estimates. Now, a bank loan, well, it's going to be derived based upon the number of years and the interest rate. So those numbers in the future will be known. But typically you estimate in a project future costs and benefits. So I'm going to give you these formulas. They can be derived. I'm not going to derive them for you. But basically, if you have a future amount, this is the formula to calculate an equivalent future amount if you have N payments of A. Or conversely, if you know a future amount, you can convert it into N payments of A. So let's go back to the cash flow diagram here. We can convert these N payments of A into a single payment F at time period N using this formula right here, 4.4. So let's look at an example here. We have $500. We're going to put it into a credit union at the end of each year for 5 years. How much will you have after the 5th deposit? Okay, so notice this cash flow diagram here. So today is right now. We're not putting $500 in today. We're putting it in one period from today, in this case 1 year from today. And notice that F is at the same time as the last payment. F is at the same time as the last payment. So there's two ways to do this. We can actually use the formula, or we can use the future value function. Now this describes the future value function, but let me show you through an example in Excel just so we can see this. So, cut this out. The interest rate is 5%. We'll pop into Excel. Oops. So I'm going to put in here the interest rate equals 5%. Okay, and what we have is the following cash flows. We have end of year 0 through 5. And our cash flow is going to be 500 each period. And what we want to do is we want to calculate an equivalent future cash flow F. So if we use the formula, I'm going to use the future value formula. Equals FV. Okay, the rate is the interest rate. The number of periods is 5. And the payment is 500. So we can just hard code 500 in there. Or I can reference a cell over here in column C. Any one of those would do. But let's do 500. Okay. Those are all that are necessary for using the payment function. We can ignore the last two terms there in square brackets. So this gives us, remember it flips the sign. Using Excel from last lesson, the sign is flipped. So if we don't want it flipped, we can either do this. $2,762.82. Now let's look at another way to do this. Let's look at the future value function where future equals P times 1 plus I, 1 plus I to the n. So we can do that right here. What we can do is the future value at year 5. Okay? And so this is going to be 500. Let's give these 2 decimal points just so we don't get messy. Okay, so this is going to be 500 times 1 plus 5% to the 1. Oops. Sorry. $525. We're taking it forward 1 period, from the end of period 4 to the end of period 5. That's this one here. This one here, end of period 3, is to the 2. The exponent is going to be. This is to the third. Now I could obviously have done this a lot more quickly with a copy command and tagging some cells. I'm trying to do it so you can see each step. So this period here, time period 1, its value at the end of time period 5 is going to be 4 time periods in the future, right? We take it forward 1, 2, 3, 4. So these are the individual components, and we can sum them up, and we get the same $2,762.82. We can do it either way. So we can use the formula, or we can do it explicitly. Now, you're going to see in most engineering economics textbooks that the formula is used, and there's nothing wrong with using the formula. In industry, I tend to see things done this way. So this is more typical. So again, the value of this $500 at the end of period 1 is $607.75 at the end of period 5. And so that's what each one of these components are. So this is the detail. And if you actually took this formula in the general form and took limits, you would end up with the formula that we have right here. So it's derivable. Sometimes I do that, but this basically shows the components of this using an Excel spreadsheet. So let's say we have a similar thing. You want to save some money, and we are going to deposit $685 in the bank and then $375 monthly. How much will you have after 48 months? So let's just do this. So we have a similar example to the prior one. However, we have 48 deposits. And we're going to make an initial deposit. Now I want to show you, because this is not intuitive, so we need to be really careful about this. So let's use the future value formula. Okay. We know our interest rate is, it's 6%. Now it doesn't say per year, so we assume per year. If it doesn't say, we assume per year. 6% per month. So the rate is 6% per month. So we can do it that way, or we can put 0.5% in, or we can put 0.005 in. Any one of those will work. Number of periods, it's 4 years, it's 48 periods. The payment, we're going to deposit $375 every month. Oops. $375 every month. The present amount, we know it's $685. Is it positive or negative? Well, let's just see. Okay, let's flip the sign on this thing so we're not dealing with negative numbers. Now this present amount is it's the same sign as the $375, right? So if I were to make this present amount negative, this is what comes back. So the correct value is this one. And I'm going to delete this right here. And so I just want you to understand that these signs need to watch these signs and be very cautious with them. But in the future value formulation, the payment and the present amount are the same sign. I mean, they don't flip on each other. And I'll be posting this worksheet to Canvas. So this can be done multiple ways. We can do, let me show you a different way that we can approach this. So here's the one way and one step. But I think that's the best way to think about doing it. Again, we could brute force it and have 48 cash flows, actually 49 periods, because we got a period 0 with these $685 in it. But it's easy to do in Excel. There's a lot of dragging, but that's just an alternative way to do it. I have no preference, whichever way you're most comfortable with solving these problems. So let's look at this. Let's look at this problem. We put $200 at the end of each year into a bank account for 5 years. We're going to earn 6%. How do we find this value? Well, we would pop it into Excel or we would pop it into the formula. It's highly unlikely that it's going to be the alternative A we can throw out. My instincts are alternative B we can D we can throw out. I would think it's either going to be B, C, or E, and we need to pop it into the formula. We pop it into the formula, and we get it's $1,127.42. Now, here's another way to look at these things. And suppose you want to know how much you need to put into the bank. You want a certain amount at the end of a certain period. So let's look at a new function here, okay? So we know that we want $1,000. So your future value your interest is basically 6% per year. And your number of periods, 1 year. It's actually 12 periods. So we have a new function here. It's the payment function. And so we use PMT, and the rate is going to be 6% divided by 12, or 0.5% per month. How about if I put it in as 0.005? But it's basically 6% per year, or 0.5% per month. Number of periods is going to be 12. Our present amount, we don't have a present amount. So the value, we have to enter a value there for it's 0, so it's 0. We have a future amount. We're looking for a future amount, and that is going to be 1,000. Now again, it flips the sign, so let's make it. So this is telling us we need to deposit $81 a month if we're going to earn 6% per year compounded monthly to have $1,000 at the end of 1 year. And so you can use this for planning. I use something similar planning for my kids for college, where I said I need to have so much money when they were 3 years old, 15 years from now, if I want to send them to a university. How much do I need to put in the bank every month to have that? And yeah, the interest rate is not absolutely known, but it is you can get a good estimate of what the interest rate is going to be. One thing I want to caution you here is get very, whoops, that is G7. Get very familiar with, after you've entered the rate and the number of periods, the direction of the signs here, because Excel has its nuances and it may be expecting a present value to be negative. If you start including all of these terms, it's not a big deal for this one because we don't have a present amount. All we have is a future amount. But when one of these values isn't zero, you need to be sure that your signs are in order. Now, you can do this with the formula. Let's look at the formula here. And so that is the way you calculate the annual payment for a future amount, is with this formula. So here's the 8107 that we just derived. Now, if you think of the formula F equals P times 1 plus I to the n, it's very easy now to calculate this in terms of a present amount in an annual payment, or calculate an annual payment based on a present amount, or a present amount based on an annual payment. And so this is the formula that is used, this top one, 4.6, is the formula that's used to calculate loan payments. So for example, this is exactly what that loan payment was, where I showed the different four methods to calculate repaying a $5,000 loan. And so it's a $5,000, life is 5 years, interest is 8%. How much must be saved annually to recover the investment? Okay, let's just look at this, because this is how you calculate payments on a loan. Okay, so we use the payment function. And the interest rate is going to be 8% per year. The loan life is 5 years. This is an annual payment. The present amount, the amount we want to recover, is $5,000. So notice this difference between calculating this payment here, and then we don't have to include the future amount because it's going to be zero. So this is how you calculate the repayment on a loan with uniform payments. Now notice the difference. This is a future amount, and we have to hard code the zero in time for the payment function. Or not, sorry, for the present amount. This is the present amount. We could include a zero here. It doesn't matter. Nothing changes. So if it's got square brackets, it's not required. That, when I mentioned last time on the equivalence portion, that is how we calculate uniform payments on a loan. So this is kind of this. If you want $1 million in 40 years, and you know you're going to earn 6%, and that's, let's say you were going to put your money in a balanced fund in the stock market. How much would you have to deposit per year? So you could divide it by 40, 1 million, and you got to deposit at least 25,000 per year. Well, no, you don't. Look at this. You only have to deposit $6,500 per year. And you use the payment function. You are going to earn 6%, 40 years, no present amount, and you want $1 million in the future. So if you extrapolate that a little bit, you could put in, what is it, a little over $500 a month? Does that work? $500 a month when you get your first job. If you get into a balanced fund that you expect to return 6%, and balanced funds typically, on average, will return that, and you'll have $1 million in 40 years if you plan on retiring in 40 years. Okay, so now let's look at a couple of things here. We have a machine, and we're going to invest $30,000 into it. We're going to spend $2,000. We're going to save $2,000 a year on operations and maintenance. We're going to save $7,000. We're going to save $10,000 a year by making this investment. We're going to be able to sell it for $7,000 at the end of 5 years. What is its present value? So I want to take it through you step by step, because this can get really, really detailed here. And I'm going to break it down into its components. Oops. Okay, so let's look at the initial cost. Now let's look at the operating and maintenance. Savings, and your salvage value. Okay, and you can do this whichever way you're most comfortable with. But for now, let's look at the signs. The spendings are negative and the savings are positive. So we're going to spend $30,000. That's why I put commas in. And our operating and maintenance costs are going to be $2,000. Our savings are going to be $10,000. And our salvage value that is going to come at the end of year 5 is going to be $7,000. So this is our series of cash flows. And let's look at the present value of each of these. So the present amount. So in year $0, $30,000 is going to be $30,000. In year $0, this series of cash flows, we can do it several different ways. Well, let's use the present value function. And our rate is going to be 10%. Our number of periods is 5. And our payment is going to be $2,000. Now notice that flipped the sign. So we know it's going to flip the sign, so we want it to be negative, right? We know that this has to be negative. I'm just trying to, so you just need to be aware of this in Excel. So let's look at this. So $2,000 at the end of each year for 5 years is equivalent to $7,581 today. We're going to do the same thing for the savings. And so this is going to be the present value of, now we should be doing, I should be putting an interest rate up at the top and just entering it one time. It's always good to only enter numbers one time. It's going to be $10,000. I think it's just better to put 10,000 in here. And we know it's going to flip the sign. So I'm going to make that a negative. So the present worth of $10,000 per year for 5 years, in year $0 is $37,900. Now, the salvage value is going to be worth, and again, we're going to flip the sign here. The rate is 10%. Number of periods is 5. The payment is going to be 0 for the salvage value. And the future value is going to be 7,000. Oops. Okay, I'm going to have to fix that. 10%. And so the total present amount is going to be the sum of these. $4,672.74. Let me just make sure I haven't made a mistake here. That works. Okay. Okay, so this is one way to do it right here. So that's one way to do it. Typically, what happens is, we have a thing called the cash flow column, or net cash flow. And that's just going to sum it across. So in year 0, it's just the $30,000. And these are our net cash flow. So this is why it's important to have your signs directionally accurate if you're just going to add across. Now let's look at a present value factor. The present value factor is 1 over 1 plus I to the n. Okay, so this equals 1 divided by 1 plus 10%. We're going to raise it to the nth power. N is over here, our end of period. Let's give it a few decimal points. And so this is the present value factor for each one of these periods. So now we can calculate the present value of the net cash flow. And this is P equals F times 1 plus I to the n. So this is simply column G times column H. And so $8,000 1 year from now is basically $72.72 today if your interest rate is 10%. And guess what? We sum this up, $46.72.74. So the reason I've shown it to you in two different ways is because a lot of textbooks will take this shortcut method, but the real world does it this way. And I think that you're going to be a lot safer if you start formulating your problems in this manner. Either way I'm fine with, but this is typically how it's done in industry. Okay, so this basically has this method here is basically the shortcut method. They netted the 10,000 and the 2,000. Now, if you want to take this and you want to find out what the rate of return is, and I'm going to get into this in the future quite significantly, but let's say we have the same same set of facts. So I'm going to go back into that Excel spreadsheet. Historically, what we used to do before Excel was we would have to, this is, if you plug the formulas in, you cannot find a tight answer for this answer. So to find the rate of return, you would have to test different interest rates, home in on one, and then interpolate. So that's not the way the real world does it. So if you want to find the rate of return is where the present worth equals 0. Okay. So let me just copy this over here. Okay, same thing. I'm going to use the interest rate. I'm going to make it 10%. Okay, and instead of hard coding 10% into the PV factor, I'm going to refer to this cell. Okay, and so you could say, okay, well, we can just tinker with this. I want the present worth to be 0. That will give me the rate of return. 12%, 20%. I think you saw the answer, 15.4%. That's effectively 0. Let's go back to 10%. So there's a couple ways to find the rate of return. We can use goal-seek. And we use goal-seek data what if analysis, goal seek. And what we want to do is we want to set this value, the present worth of the project, to 0 by changing the interest rate. And look at that. It comes back to 15.38%. So that's one method to do it. The other method to do it is with the IRR function. And we utilize the IRR function on the net cash flow, not the present value of the net cash flow. And we just highlight the vector of values. And this is our interest. So our internal rate of return is that. Our present worth is that. So when they ask for a rate of return, and many projects are measured by their rate of return or their internal rate of return, it's the interest rate where the present worth equals 0. So this basically takes you through the old method of solving. I should have deleted the slide. You'll never do this in industry, but basically you try different methods. So at 10%, it was $4,674. At 15%, it's $296. At 18%, it's negative 19. You interpolate between the two, and you get 15.4%. And that's where the present worth equals 0. So if we want to invest $75,000 to save $9,000 a year for 15 years, what is the project's rate of return? Well, what we can do is we can do end of year 0 and we have a cash flow, and we're going to invest 75,000 to save, was it 9,000? 9,000. We're going to invest 75,000, so that's a negative 75,000. And we can use the IRR function. Okay, if your savings amounts are all the same, and they are in this case, note that they were not in this case, they were different, but if they are all the same, you can use the rate function. And the rate function is you put in the number of periods, 15, the payment, which is 9,000, and the present amount. And this is where you need to be very careful. If I put in 75,000, it doesn't work. So it's expecting a negative 75,000. So I can use the rate function because all the annual cash flows are the same. So the answer to this is 8.44%, and that's using the rate function. Okay, so let's look at this problem right here. How are we going to solve this problem right here? Okay, so we know what the car costs. We have 48 payments of $398. What is the monthly interest rate? Okay, so we have the cost, payment, life. The cost is $15,732. Payment is $398. The life is 48 months. Let's make these dollar signs. Okay, so the monthly interest rate, we can use the rate function for this because all the payments are constant. And we know it's a monthly interest rate because we're using months. Okay, where the payment is monthly and the life is 48 months. So we're going to use the rate function. And the number of periods is 48. The payment is 398. And the initial cost is negative $15,372. And so our monthly interest rate is 0.82%. That's per month. Our nominal annual interest rate is going to be 12 times that. Let's make it a percent. Our effective annual interest rate, and this is 1 plus your nominal rate divided by 12 to the 12th minus 1, 10.32%. Well, I sure hope I did that right. Okay, or you can use the effect function. Oops. You put in the nominal rate, 9.87, and the number of periods per year, 12. %10.33%. So if we're going to do this problem, I took you through the steps in doing it. This shows you how to do it in one step in the various methods to convert from a monthly interest rate to an annual effective rate. Now, this is where things get a little bit messy, when the formulas don't quite work right. So if we want to compute a future amount, if we use the F given A formulation, we will compute an F at the end of period 3. The formulation does it at the end of the last cash flow period. So we've got to move things around a little bit here to solve for this. So we can do it several different ways. We can compute a single amount at the end of period 3, then bring it forward 2 years. We can compute a single amount at time period 0 with a P given A formulation, then take that forward 5 years. Or we can do this individually. So there's multiple ways to do this type of problem. So the key thing is to lay out the cash flow diagram to understand where your cash flows are coming from and the time involved. So this is method 1. What we're going to do is we're going to take each one forward individually. So we're going to take F1 is going to be taken forward 1, 2, 3, 4 years. F2 is 3 years. F3 is 2 years. So we're taking this forward 2 years. Taking this forward 3 years. Value $4,592. That's method 1. Method 2. We compute F3 and that's the value of these $100 payments. I'm sorry, 1,000. That should be 1,000. What did I do here? Yeah. Sorry about that interruption. This should be 1,000. I'll fix that. So we're going to compute F3, and so the value of these $3,000 payments at the end of period 3 is $3,472. Then we take it forward 2 periods. So we're going to take $3,472 forward 2 periods. So we're treating this as a P, and this is an F. So this is P times 1 plus 0.15 squared. We get the same value. Or method 3, well, this is basically the same thing. This is method 3. Solution 3 is doing it in Excel. So I want to stress there's multiple ways to do these problems. And whatever way you're most comfortable with, which makes the most sense to you, is the way to do it. My instincts are that this is probably the one that is the easiest to visualize, taking each one of these individually forward. This one 4, 3, and 2 years. But it's whatever you're most comfortable with. I'd say doing it in one step is the one that you may be comfortable with, you may get comfortable with. It's easiest. It's also easiest to make a mistake. So let's look at this problem right here. We're basically saying we want to put money in a savings account today. We want to support 3 withdrawals, 1 at the end of year 2, end of year 3, end of year 4. So how do we solve this problem? Interest rate is 15%. Okay, let's see what we can do here. Okay, when I don't like that. Change the dollars. So Excel, when you use some of these formatting systems, will treat this as a 0, this is 0. So this is P equals F over 1 plus I to the n. So this equals 1 divided by 1 plus I raised to the nth power. The present value of the cash flow is simply the amount of the cash flow times the PV factor. And so 2,000 in 2 years is the same as 1,512 today, 3,000 in 3 years, 1972 today. So we would need to deposit $4,628 today. And so effectively what I did was, I did it in one spreadsheet, but this is individually what I did with each one of these. And I believe this is the best way to approach this problem. Okay. There's another way to do it here. You could take them to everything to the end of period 4 and then convert it back to time period 0. That's perfectly fine if you're comfortable with that. I think this is just another way to look at it, but I think this is just more confusing. I think if you get yourself familiar with methods 1 and 2, you're perfectly well armed to attack these kind of problems. Solution 3 is another way to do it. You're basically converting a piece of it to period 1. You're turning it into two problems. One, which is an annual series of 2,000, which you're converting the present worth of, and then one, which is a end point of 1,000 at the end of period 3. I just think this is way too complicated for this type of problem. But this is another method, if you happen to have the textbook, that it'll take you through. And this, okay, so this is the multi-step problem. This is effectively what I did in my problem, in my solution. Let me show you. You can see the 15, 12, 29, 15, 12, 29, 1972. So this is effectively the way that I did it here. The way that I did it here in this Excel worksheet is the way these things are done in industry. So I would strongly recommend doing it that way. So let's look at our Excel formula here. This is F and P. This is A and P. F and A. I think you're going to be safest using the formulas and the Excel functions. This is more of a shortcut to, if you get into the graduate class on this, to understand exactly the derivation of these formulas. Specifically this formula here, this last one gets real messy. There's problems in the textbook that I recommended that utilize this formulation, but I don't think this is really necessary for you to understand what's needed for this course. Okay, so when you do engineering economic studies, when you do project justifications, it's all done in Excel. It's almost never done by hand. What you do is you build a table of cash flows. You formulate the answers you want to find the present value, net present value, or internal rate of return. These are our two performance measures typically. You make graphs, you do what-if analysis. And so these are the different spreadsheet functions. We use the PV function to find a present amount, the future value function to find a future amount, the payment function to find an annual amount, the number of periods function to find n, which you can back solve for n, and the rate function to find an interest rate. I also showed you the IRR function to find the interest rate, which is more typically used. The functions you're going to use most of the time are going to be the PV function, the payment function, and the rate/IRR function. So if I asked you to build an amortization table, we're going to, what do I mean? So this is what we're going to do. So let me build the table. And I'm going to be a little bit more detailed than the example in the slides. So let's go with the interest rate equals 10%. And we're going to have the loan amount $4,000. Okay, so what we're going to do here is we're going to have year 1, 2, 3, 4, 5. We're going to have beginning balance. Okay, that's going to equal $4,000. Just trying to get the dollar sign in there. Okay, let's get that. And we're going to have the interest. Well, we don't really know the interest yet. Well, let's look at the payment amount. We're going to make 5 uniform payments. So we can use the payment function. And the rate is 10%. The number of periods is 5. And the present amount is $4,000. Is that right? We'll make sure that's right. Before we go any further, 1,055, okay. Okay, so our payment is going to equal $1,055.19. And that's going to be for every period. And so our principal or interest payment is going to be 10% times the balance at the beginning of the period. So our interest payment is going to be $400. Okay. Now we're making a total payment of $1,055. So our principal payment, the amount of the money we're going to pay on the loan, is going to equal the total payment minus the interest payment. It's going to equal the total payment minus the interest payment. And so our ending balance is going to equal our beginning balance minus our principal payment. So that's year one. Year two, our beginning balance is going to equal the prior year's ending balance. Principal payment is going to be the same. Our interest payment is going to be 10%. Let me line this up better. Our interest payment is going to be 10% times $3,345. Our principal payment is going to be $1,055 minus $344. And our ending balance is going to be. So now after you've done the second row, you can, if you've tagged them properly, you can drag it all the way down. And the reason this is red and in parentheses is that somewhere out there it's slightly off by a fraction of a cent. But this is an amortization table. This is the amount you pay each year. You can clean it up a little bit, bold, center. Amortization table. Notice it's slightly different than what's shown here. I like the method that I do. It's got a little bit more detail. It's very easy to see what's going on. But basically, fundamentally, the interest and principal are the same as in my table. I just have a few more little details in it. If you start playing around with various functions, you're going to find something called the NPV function. And I'm going to use it later on, but I want to caution you that this is probably the one function that students use incorrectly the most. And the NPV function is for periods 1 to n. So the first cell is not period 0. So I'll go through that in an example, but it's like, and I'll specify it when I use it in videos later on, but just be super cautious using the NPV function. You don't have to use it. You can do perfectly fine without using it. It is a shortcut, but it is not the PV function. So the PV function is something completely different than the NPV function. So let's look at this series here. I'll give you an example here, and that'll be pretty much it for the this video. So here's our cash flows. Minus 250. Okay, the interest rate is 5%. Let's do this the right way. Present value of the cash flow is simply that times that. So the present worth is simply going to be the sum of that. So we know that the answer is 1647. Now, if you use the NPV function to find this answer, and you say equals NPV of this, I'll put the interest rate in. Sorry. %. You get $15.69. You don't get 1647 because it's treating this as period 1. So if you look at 1647 divided by 1.05, that's what it's doing. So this is incorrect. What you want to do is you want to take this plus NPV at 5% of these cash flows. And that is the correct way to do it. So it treats the first cash flow as time period 1. Whoops, that shouldn't be a percent. Don't know why that did that. Anyway. What's going on here? Format sales. We just want 2. There we go. So this is the correct method to use the NPV function. I'm cautioning you of that because this doesn't tell you that you did it incorrectly, and the number is close. Okay, so just need to be super careful if you're using the NPV function. And so this example here says you have to use the NPV function. You can't use the PV function when you have different cash flows. Well, that's true, but what I want to emphasize here is that industry analyzes problems this way. So you're going to want to consider analyzing all your problems this way. And so you can use the one step, but industry does it spelled out like this. This is the better way to get to this answer. So you can do it in one step. The tools are there, but this is the better way to do it once you get to industry. So that's it for this video. I know it was a long one. I'm going to post all of these 8 sheets on Canvas, and we're going to talk about project analysis and how we use present worth analysis in our next video.